Okay. Yeah, he's already decided he wants food. Off he goes. Okay. Yes, that's one of them. Perhaps over the course of, yeah, exactly nine days. Okay, come on, Gobble. Come on. He's gonna go find food, perhaps. Go on. Go. Okay, cool. So, yes, 8 more to go. So, we're going to talk about periodic trends. Let's see. Okay, cool. Wait a second, who's feeding back? It's one of you. Ah, it's Marissa. Okay, Marissa, you're getting muted. Okay, cool. So, exactly. So, cool. Periodic trends. So we're going to be able to come up with, so that was one pattern we saw. We're able to see the number of valence electrons in a particular group by looking at their electron configuration. We're going to talk about a couple of other things. So we're going to talk about size. We're going to talk about electron affinity and then electronegativity. We're going to talk about all of these things. And then the last one, ionization energy. So at least hopefully the first one should be familiar to you. You probably know what size means because, you've been through kindergarten. So size, how big something is, right? So we have another one. We're going to be talking about metallic character. Yeah. Okay, cool. Size. So size. Who can define size for me? This is still 4, Marissa. Yeah, exactly. This is the last part of 4. Alright, so we're going to be looking at various atoms, and we're going to be able to compare their sizes, okay? So, if we just look at sodium, I'm going to just draw those kind of same type of things we've been looking at. So sodium, there's sodium. How do we know it's sodium? Because there's all these electrons here. You remember this type of drawing we did last time? So this is sodium. And let's look at potassium. Alright, I want you guys to guess. Sorry, this is potassium. Guess which one of these is bigger. Yes. Are you just guys saying K to me as if you don't care in a text message? I send you this paragraph and you guys just say K? That's it? Heartbreaking. Okay, cool. So, yeah, potassium. Cool. So, definitely bigger. We can see that, right? We see that this guy has more rings around it. We see potassium has 4 rings. It's got 4 shells, whereas sodium has 3 shells. So the first conclusion we're going to be able to come up with is that more shells is bigger. So potassium is bigger than sodium. We're going to see, Robert, let's just look at number of shells right now. Alright, so we're going to see that if you look at the periodic table, let's see how sodium and potassium are related. Sodium and potassium are these two. We see that potassium is right underneath sodium. Alright, so they both have 1 valence electron. But potassium just has one more shell, basically. And so therefore potassium is going to be bigger. If we think about lithium, where do we think lithium is going to fall? Is it going to be bigger than potassium, smaller than potassium, bigger than sodium, smaller than sodium? What are we thinking about lithium? Smaller than what, Robert? I like your ideas, Elza. Yeah, then both, right. So, yeah, exactly. So it's definitely smaller than both because it's really the same thing, except now it only has 2 rings around it, right? So we have little lithium over here. Okay, so of course these are exaggerations, but we can see that lithium is the smallest one of those 3. Alright, because it has fewer shells. So we're going to see if we go down the periodic table, that means our atoms are getting bigger. Alright, so whenever we're comparing elements, we just take a look at the periodic table. If we were to compare manganese and technetium, we're going to say that manganese is smaller, okay, than technetium is. Okay, so every time you go down on the periodic table, you are getting bigger. Well, considering that nothing is above the F block, technically, remember that the F block has that kind of just like stretched out portion. The F block does not have things above it or below it, so if you're comparing terbium and berkelium, for example, that's what you can do. You're just comparing up and down right now. Okay, and really no one cares about the size of these ones down here. They're all the same. Nobody cares. We're caring more about, stuff that's more commonly used. Like, nobody uses europium for stuff. Like, these elements are so low in abundance that they're not really going to be talked about in this class pretty much at all. So you probably won't even talk about them in 102. So don't worry about the F block. Okay, but the higher you up on the periodic table, the smaller you are. The lower you go down, the bigger you are. That's the first part. Okay, does that make sense? Hopefully it does. Okay, cool. If we move on, let us compare these 2 guys. I'm not going to make the difference obvious to us. Okay, so we have now... What elements are these, by the way? He and H. Yes, you're right. This is hydrogen, this is helium. Yes. So, how do we know that? Because of the number of electrons, right? So, if we look at these, they both have the same number of shells, right? They both have just 1 shell. If we look at them, what's the charge of the nucleus in hydrogen? Just the nucleus itself. Assuming there were no electrons. Positive what? Positive 1, right? Very good. And how about helium? What's its nucleus charge? Positive 2, right. So, if you are some little negatively charged dudes, or dudettes, my apologies, or third duds, I guess, I don't know. Cool. If you are an electron, which one are you going to be more attracted to? The positive 1 or the positive 2? Yeah, right. So electrons are going to be more attracted to number 2. And therefore, if they're more attracted to that, are they going to be closer or further away? Yeah, exactly. So we're going to see that if we just kind of like zoom in, this is totally like fake, but these ones are going to be closer to the nucleus. I don't know if you can see that, but this one should be smaller. Okay, this one should be bigger. Okay, we're going to see that the next to each other elements, when to the right or to the left, we're going to see the one that has more protons is going to pull the electrons in more, making it smaller. Okay, let's do another pair of them, okay? Let's do oxygen. And fluorine. And not neutrons, protons also. Neutrons don't have any charge. Yeah, so we're going to see they both have two shells. Oh, I'm sorry, yeah, this is fluorine and this is oxygen. Sorry, Marissa. So, this has 9 protons rather. This has 8 protons. So that means that it's a +9 charge, or a +8 charge. And so Zoe's absolutely right. This one should be smaller. Okay? Because more protons in the nucleus with the same number of shells is going to pull those closer together. Okay, going to pull them in towards the nucleus. Pulled in toward nucleus. All right, so hopefully that makes a little bit more sense. So we can see that as we go to the left on the periodic table, wow, let's see, that's a big manual, isn't it? Periodic. There we go. You see, I fixed it. As we go left on the periodic table, we're going to see that things get bigger. Okay, so if we go from fluorine to oxygen, oxygen's bigger. Okay, because it's not pulling those electrons in as tightly. No, I did, Robert. But I phrased it as pulling amen well. Yeah, whatever. Okay, cool. So, we also saw before that as you go down the periodic table, you also get bigger. So, if we had to guess, what is the biggest element on the periodic table? Yes, absolutely. The biggest is francium. Not quite, Elsa. Because remember, if we go down on the periodic table, we're also going to get bigger. So since hydrogen has things below it, we're going to go... What do you mean you? Oh, no. So remember, if we go to the left, Robert, go to the left, you get bigger. So francium is our biggest. Okay, so that is this guy down here. I'm sorry, this hand. Yeah, not that one. Francium is the most left and the most down on the periodic table. That means it's going to be the biggest one. The biggest of all the elements, francium, right here. Alright, conversely, the smallest element is going to be at the opposite side. Smallest element should be helium. Absolutely right, Zoe. Very good. Okay, so biggest is francium, and the smallest one is going to be helium. So helium is just going to be this little dot. Helium is smallest. Okay? So that's a tougher question, Robert. Second biggest, to be quite honest, it could be either radium or cesium. I don't know off the top of my head, but it would be one of those two. Okay, because remember we can either go down or to the left. So the opposite would be going up or to the right. And so we have multiple options there. But we can say without doubt that francium is the biggest and helium is the smallest. Okay. All right, Arpin, here we go. Is that enough? Yes. And okay, here we go. Exciting times. This is hydrogen, lithium, sodium, potassium, rubidium, cesium, and of course francium. Which one's the biggest? This is for Zoe or Elza. You tell me which one's the biggest. Yeah, Arpin, you're right. I know it helps to see it in picture form, but so remember, the farther down we go on the periodic table, farther down, the bigger we get. Okay, down is bigger. All right, and then to the left is bigger. Okay, there's two trends. Zoe, that's a very good question. Between hydrogen and neon, it's not exactly obvious to us. Okay, because one of those is more to the left, but one of those is more down. So that is, to me, an unfair question for me to ask you. Okay, I could ask you between neon and chlorine, for example. I could ask you which one's bigger. But I cannot compare fluorine and argon. So I can compare diagonally this way. Sorry, I guess you couldn't see that. Diagonally that way. I would say hydrogen's smaller than neon. Nickel and calcium. You can do that. Calcium is bigger. Yeah. Yeah, so Arpin, hydrogen was bigger than helium, but it's going to be smaller than lithium. If you want to really know, let me see. I think I can just, let's see. List of atomic radii. Okay, cool. Okay, here we go. If you really want to see, well, whatever. They're there. Okay, comparing, neon is definitely going to be bigger than hydrogen. Okay, I have looked it up. Cool. Okay, so those are our trends, okay? So, to the left and down, you get bigger. Okay, that is the trend we're looking at. Okay? So, alright, moving now past this hideousness. I see you're typing something, Zoe. I'll wait a sec. Correct. So these trends are pretty reliable. So Zoe, it's hard to say. Typically, yes, that is the case, but I don't want you to have to worry about that. So yes, technically going down is a bigger effect than going to the left, but yeah. Don't even worry about the F block. You guys are just crazy. All right, we're not going to worry about the F block. Okay, let's do some comparison. How about we have these 4 elements? I'll re-erase this one. Which one of these is the smallest? And which one's the biggest? Very good. Smallest is fluorine, biggest is sulfur. Okay, and if we were to compare oxygen and chlorine, we couldn't. Okay, we do not know from our trend if oxygen is bigger than chlorine is. Okay, so I will never ask you that. However, I could ask you between fluorine and chlorine. That you should be able to do. And I could ask you between oxygen and sulfur, but I cannot ask you between oxygen and chlorine. Okay? So we're always going to follow the trend. Okay? All right, let's do another trend. So our second one, if we go back up to the top, we want to talk about electron affinity. Okay. Affinity, okay. What does the word affinity mean? Does anybody know? Just English test. Doesn't mean image. Yeah. Tiffany's got the right idea. Affinity is how much you like something, exactly. Yeah. How much an element wants electrons. Yeah, it's a liking for something. So this element, which an electron affinity will be how much an element wants to get an electron. Alrighty. So let's go ahead and... What about it, Zoe? I see. Very good. Okay. Cool. So the thing wants electrons. Yeah. Cool. So let's have a look. I'm going to tell you, pro tip, everybody. Everybody wants to be a noble gas. All right. So this is just effective chemistry. All the elements want to be noble gases. We all do. We should all aspire to be nobility. Wouldn't that be nice? So let's compare 2 elements. Let's compare sodium versus fluorine. If we look at their electron configurations, we're going to have 2s2, 2p5, and this one we're going to have neon 3s1. Okay, remember, what did all the noble gases have as their electron configurations at the end? What did they all kind of have as valence electrons, do we remember? They all have 8 valence electrons, right. So, if we look at fluorine has how many valence electrons? 7. Remember, Stanville, we have to count the S1s as well. Okay, so if it's got 7 valence electrons, how many electrons would it need to get to 8? Okay, I like that. 7 valence electrons, so it needs 1. Sodium has how many valence electrons? It's got 1 valence electron, so how many is it going to need to get to 8? Oh, yikes. Alrighty. So, which one of these would you say is closer to becoming a noble gas? Yes. So fluorine is closer to being a noble gas. And so if you imagine, fluorine is right at the end of its journey, it's like, I'm so close to having 8, I just need one more. Versus sodium's like, oh my god, I just started gathering electrons, I have to gather 7 more still. Which one of these two elements do we think really wants to get electrons? Yeah, so we're going to say that this really wants the one more. All right, and if this were to get one more electron, what would its charge be? We're going to see, Zoe. Hold on to that thought. Yeah, so the charge would be -1. Okay, and if this guy, if it got 7 electrons, it would be -7, right? If I tell you that higher charges are typically less stable, which one of these is the better one to have? Like, if atoms don't really want charges, which one is better? Why are you saying sodium? Seven versus 1, which one's the bigger charge? In terms of magnitude, not necessarily direction. Yeah, sodium's got actually the bigger charge. Right? -7 is actually worse than -1. Elements don't want to be charged. So, -7 is going to be worse than -1. Does that kind of make sense? Okay, think about it this way. Would you rather juggle 1 flaming torch or 7 flaming torches? Yeah, you'd rather have 1, right? 1 is easier to handle. All right, having 7 extra torches is going to be a pain. It's going to be impossible. But 1 we could maybe manage. So this is going to be the better situation. And we're going to see that fluorine is going to have our highest electron affinity. It really just wants 1 more electron. Okay, it's so close to getting to that magic number of 8. Okay, sodium is really far away, doesn't really have much motivation. Okay, fluorine's about to cross the finish line, it really wants that electron. Let's compare fluorine versus oxygen. Yes, we're going to say F is higher electron affinity. I'll write that in blue. Okay, oxygen versus fluorine now. I'm just going to write needs 1. This one needs 2. All right, is that part okay if I'm just telling you needs 1 electron versus needs 2 electron? Alrighty. Go ahead, Tiffany. Yes, you're going to be right. Another way we can explain this is that the nucleus, remember, is a charge of +9 for fluorine and +8 for oxygen. All right, and so if we're thinking about, 1 electron, if there was only 1 electron available, is it going to go to fluorine or to oxygen? Yeah, it's going to go to fluorine, not only because fluorine has the higher charge in its nucleus, more positive is more attractive, but it also only needs 1 to be stable. And so it's going to kind of be a win-win this way for the electron to go there. So we're going to say that fluorine, again, has higher affinity. electron affinity. Alrighty. Alrighty, let's do one more comparison. Let's compare these two guys. Okay, I'm going to go ahead and draw them out here. Cool. Yes, Tiffany, you are going to be right, but let's see why. Okay. You are the electron. We both need one this time. So you're both just so close to getting to that magic number of 8. Alright. Okay, we know that this guy has 9 plus. Wow, this guy has 17 plus. But Tiffany, your prediction that fluorine is going to win was correct. Samville, because these both have 7 valence electrons, if they want to get to 8, they only need 1. Okay. So, you're the electron. We think about it, yes, chlorine does have more positive charge. Okay. However, if that electron goes in, I'm just going to draw that extra electron. Right? Which one of these electrons is going to be closer to the nucleus? Indeed. So because fluorine, exactly, it has fewer shells, it's very close to the nucleus. Alright? So, fluorine will win again. Closer to nucleus. Higher affinity. In fact, we are going to see that fluorine has the highest electron affinity. Alright, and we saw that oxygen had lower. Yes, very good, Elsa. You're absolutely right. On your periodic table, as you go to the right and up, you're going to be higher electron affinity. That's absolutely correct. It is the opposite of size. So the smallest ones are going to be the most have the highest electron affinity. Alright, consider the smaller the atom is, the closer that electron is going to be able to get to that nucleus. Alright, so smaller things are going to win. Okay? Fluorine is going to be our highest electron affinity, and what's our least electron? Which one has the smallest electron affinity? Francium, indeed. Doesn't want one. Okay, so francium does not care for electron affinity. Alright. Are we good so far? So this electron affinity trend was the opposite. Alrighty, so another trend. By the way, I'll just tell you right now, electronegativity is the same trend, okay? I'm just going to write that here. I'm going to talk about electron... yes, that's correct, Robert. I'm going to talk about electronegativity next time, but the trend is exactly the same. Okay, so both of these electro things, fluorine is going to be our most, francium our least. Okay, we're not even going to talk about the noble gases. They're already noble. They already have 8. They're not going to want any more electrons either, but we just typically don't even consider them a part of this. All right, now let's do the opposite trend. Let's look at ionization energy. Which is the energy needed to remove one electron. Let us compare our sodium versus fluorine again. Okay. If sodium loses an electron, what will happen to it? It will become positively charged, that's correct. But in terms of what's its electron configuration going to be? Yeah, which is the same as neon, right? You're absolutely right, Stanville. Aha! So, sodium, if it loses one electron, is a noble gas now, in terms of its electron configuration. If fluorine loses one, it's even further away from being a noble gas. Remember, fluorine was so close, if it just got one more electron, it would become a noble gas, but it's going to have to lose 7 of them overall to go the other direction. So if we think about this, which one of it is it going to be easier to do? Is it going to be easier to take the electron from sodium or from fluorine? I agree, Zoe. So, we're going to see that this is lower ionization energy. Okay, this one is higher. Easier to remove. Hard to remove. Okay, it always takes energy to remove an electron, by the way, but it takes just a little bit to get from sodium, but a lot to get from fluorine. All right, if we consider it, say I'm extremely wealthy. Wouldn't that be nice? Okay, I'm fluorine. I'm really, really small. I live in a tiny apartment, and I have all my money in my one studio. You know, I have it all around me. All right, I'm francium now. I have this huge mansion. I'm a huge atom. And I'm going to take that money and put a little bit in each room. Okay, so comparison. Fluorine, tiny studio apartment. All the money right there. Francine, really big mansion, 50 rooms with some money in each room. I am too cheap to purchase a security system. So which one do you think it's going to be easier to steal from? If you wanted to steal my money, is it easier to steal from the studio apartment, which is where I am, and I'm watching and hoarding? Or is it in the 50-room mansion where it's one of those rooms that I haven't been in 3 years? Consider it, Shelby, if you don't want to be caught. You guys are terrible burglars. Oh my god. Okay, if I'm in the studio apartment and you come to rob me, I'm gonna catch you. Yeah, I mean, I have nowhere else to go, Shelby. But in the mansion, I have 50 rooms. I'm in quarantine. Come on, guys. you guys should know we're staying and sheltering in place, right? So the studio I'm watching over. I can hoard it. No, the 50-room place has the same amount of money in every single room. Alright, but some of those rooms I haven't been in 30 years. Even though I'm 30. So, yeah, I've never been in some of the rooms. It'll be easier to steal. Fine. We'll do it this way. Okay, here's the security guard. That's the money we're going to steal. Okay, security guard is in the middle. Which one of it is it going to be easier to steal one of these dots on the outside? Yeah, for sure. You just go up, yoink, and exactly, it's further away from where people are paying attention. So same idea with the mansion. If I'm in one room in the mansion, you go 20 rooms away, you can probably very easily steal money I'll never even notice. Exactly. So this guy has more rooms. Okay? That's where I was going with that analogy. Okay, time's up, guys. So I don't want to keep you past 5:30. So we'll continue this. This is the trend, though. Fluorine will have, again, the higher ionization energy, and francium will have the lowest ionization energy. So it goes up. Same as electron affinity. Yeah, that's fine, Zoe, I know. Fine, bad analogy. Alrighty, guys, don't forget you have homework due on Wednesday. You're going to take a picture of it or scan it, and you're going to submit it on Canvas. I can show you what that's going to look like. So, yeah, I know, we all do. Okay, I'm going to stop the recording because